Hey everyone, and welcome. Today, we're jumping into a classic problem from the legendary Irodov physics problem book. We're tackling problem 1.24. Now, if you've ever gone up against one of these, you know they can be a real workout. So we're going to break this one down together, piece by piece.
All right, let's get right to it. So the problem gives us this thing called a radius vector, r. You can think of this equation as the particle's GPS telling us exactly where it is at any moment in time, t. The at part handles its movement on the x-axis, and that minus bt squared j part, well, that takes care of the y-axis. Our mission is to squeeze every last drop of information about this particle's journey out of this one little equation.
So here's our game plan. First, we'll figure out what the particle's path actually looks like. Then, we'll get into the nitty-gritty of how it's moving, its velocity and acceleration. After that, we'll look at the angle between its motion and the forces acting on it. And finally, we'll wrap up by finding its average velocity and putting together a little toolkit you can use for other problems.
First things first, the trajectory. This position vector is all about time, right? But what does the path actually look like in space? To see that, we need an equation that connects y directly to x, and that means we need to kick the time variable t out of the equation.
This is a super common trick, and it's really clever. We just split the main vector equation into its x and y parts. From that x equation, it's super easy to get time, t, all by itself. Once we have t in terms of x, we just plug that expression right back into the y equation. It's a neat little algebraic maneuver that lets us switch our whole perspective.
And voila, after that little substitution, this is what pops out. We get y equals negative b over a squared times x squared. Now, if you've taken any physics class, that shape should be screaming at you. It's a parabola. And that little minus sign out front tells us it's opening downwards, just like the arc of a ball you toss to a friend.
Okay, so we know the path is a parabola. That's the what. But now we need to figure out the how. How is the particle actually moving along this path? Is it speeding up? Slowing down? To get those answers, we've got to break out the big guns of kinematics, calculus.
So, velocity. By its very definition, it's just the derivative of the position vector with respect to time. It's the answer to the question, how fast is the position changing and in what direction right now? This is an absolute cornerstone of physics.
So, let's do it. We take our position vector r and just differentiate it piece by piece. The derivative of a is just a. The derivative of negative bt squared is negative 2bt. And that gives us our velocity vector. V equals ai minus 2btj. And hang on, notice something cool here? The x part of the velocity is just a constant, a, but the y part is changing with time. Interesting.
So what about acceleration? Well, you can probably guess what's next. Acceleration is to velocity what velocity is to position. It's the rate of change. So all we have to do is take one more derivative with respect to time.
And this is where we get a really big clue. We differentiate our velocity vector. The derivative of the a part, since it's a constant, is 0. The derivative of the negative 2bt part is just negative 2b. So the acceleration is w equals negative 2bj. And look at that. The acceleration is constant. It doesn't depend on time at all. It's always pointing straight down.
This is the key insight, right here. We have an object moving with a constant acceleration that is pointed purely downwards. Does that sound familiar? It should. It's exactly like projectile motion in a gravity field, where the acceleration is always just g straight down. This abstract math is suddenly looking a lot like the real world.
Now that we have the velocity and acceleration vectors, we can start asking some more sophisticated questions. Like, what's the angle between the direction the particle is going, its velocity, and the direction it's being pushed, its acceleration? This tells us if the force is helping it speed up, slowing it down, or just turning its path.
Think about it this way. When you throw a ball up in the air, right? At the very peak of its flight, its velocity is perfectly horizontal for just an instant. But gravity, the acceleration, is pulling straight down. The angle between them is 90 degrees. But everywhere else on its journey, that angle is different. Our job is to find a formula that tells us that angle for any time t.
And lucky for us, there's a perfect mathematical tool for this, the dot product. It's this awesome operation that connects the components of two vectors to the angle between them. We can just rearrange this formula a bit to solve for the angle.
So you take the dot product of our v and w vectors, divide by their magnitudes, do a little bit of algebra, and you end up with this expression for the angle alpha. Now what is this actually telling us? Well, as time goes on, the particle is getting faster and faster in the downward direction. This means its velocity vector gets more and more vertical. So the angle alpha between the velocity and the constant downward acceleration gets smaller and smaller, heading towards zero. Basically, the force of acceleration eventually wins out and pulls the path almost straight down.
All right, we are on the home stretch. The last piece of the puzzle is to find the average velocity vector. And it's really, really important here to remember that average velocity is not the same thing as average speed. They are two different things.
Average velocity is a vector. It's defined as the total displacement, which is just a straight line from your start point to your end point, divided by how long it took you to get there. And since our particle starts right at the origin, the displacement vector is just its final position vector, r of t.
So the calculation actually becomes really easy. We just take that original position vector we started with and divide the whole thing by t. The t just cancels out, and we're left with our average velocity vector, ai minus bj. Simple as that. And of course, if we want the magnitude of that average velocity, kind of like the average speed in a straight line from start to finish, we can just use the Pythagorean theorem on its components. That gives us the square root of a squared plus b squared.
So there we have it. We've completely solved the problem. But honestly, the answer itself isn't the most important part. What's really valuable is the set of tools we use to get there, because you can use them on almost any kinematics problem. Let's recap them.
This right here is your core kinematics toolkit. Number 1. Break down vectors into their x, y, z components. It makes things so much easier to manage. Number 2. Use your calculus. Derivatives let you go from position to velocity to acceleration. Number 3. Use vector algebra, like the dot product, to figure out how vectors relate to each other. And finally, number 4. Always be super clear on the definitions, like the difference between average velocity and average speed. And that brings us to the final thought, which I think is the coolest part of all this. The abstract equation we've been playing with, it isn't just a math problem. It's a perfect description of something that happens in the real world. Think about it, a constant velocity in the horizontal direction and a constant acceleration straight down. That is exactly the motion of a ball rolling off a horizontal table in a gravity field. The beautiful, complex physics of our world can be captured in these elegant little mathematical expressions. Thanks so much for joining me.